welcome to chemistry classes by Vijay Kumar Sethi, class 11th chemistry. We will start the next unit, unit 7, equilibrium, and in this video we will discuss about reversible reaction, static and dynamic equilibrium, and equilibrium in physical processes. First come to reversible reaction. A reaction which proceeds in both forward and reverse directions at the same time is called reversible reaction. In reversible reaction, reactants are reacting to produce products and products are reacting to produce reactants. In a reversible reaction, a state is reached at which forward and reverse direction of the reaction occurs at the same rate. That is, the rate of the two opposite processes becomes same, and this state is called state of equilibrium. Clear? State of equilibrium is also attained in physical processes. Reversible reaction and state of equilibrium is represented by putting this type of arrow. Clear? Between reactants and products. For example, this represents the equilibrium between liquid water and water in the form of vapors. Clear? The same way, if we assume one hypothetical reaction A and B reactants convert into C and D products, then if there is the equilibrium, then this sign represents the state of equilibrium and also the reversible reaction. Now, types of equilibrium. Equilibrium may be static equilibrium or dynamic equilibrium. What are the differences between these two types of equilibrium? In case of static equilibrium, all the particles are at rest and there is no motion between reactants and products. In dynamic equilibrium, changes occur within the mixture, keeping the total composition same. In case of static equilibrium, both forward and backward reactions come to a halt. Halt means come to a stop. There is no reaction is taking place. No change is taking place after achieving static equilibrium. In case of dynamic equilibrium, the forward and backward reactions are going on with same rate. The static equilibrium is often applied in a mechanical context rather than chemical context. While dynamic equilibrium, it is more often discussed within a chemical context. Okay? These diagrams represent the static equilibrium. This is seesaw. You are familiar? If both the sides equal weights are there, clear? Then there is no change in this position. This is the static equilibrium. And this is the dynamic equilibrium, and I have taken the physical processes. Okay. Now in this case, this water is coming in this container, and from this step, water is going from this container. If a rate of water which is coming equal to the rate of water which is going, then we will observe that both the processes are going on, but there is no change in the level of water in this container. Okay. In the same way, this is escalator. I think you are familiar with this escalator. You can see the escalator in the mall or at the railway station. Clear? This is used for down escalator as well as upward escalator. In this case, this is a down escalator. It means escalator is coming from this to this side. And in this escalator, if any person start to go upward and maintain the speed in such a way that whatever the speed with escalator is coming down and the speed by which a person is going up, if it is same, then you will observe that escalator is coming down, person is going upward, but there is no change in the position of person. Clear? This is the dynamic equilibrium. Now we will discuss the equilibrium in physical processes. The most familiar examples are the phase transformation processes like solid liquid equilibrium, liquid gas equilibrium, and solid gas equilibrium. First come to solid liquid equilibrium. Ice and water kept in perfectly insulated thermos flask. No exchange of heat between its contents and the surroundings. At 273 Kelvin and the atmospheric pressure are in equilibrium. This can be represented like this. This is H2O as a solid, that is ice. And this is H2O liquid, water in the liquid form. The mass of ice and water do not change with time and the temperature remains constant because the rates of transfer of molecules from ice into water and of reverse transfer from water into ice are equal at atmospheric pressure and 273 Kelvin. That's why this is a equilibrium, because this is a dynamic equilibrium. Okay, both the opposite process are continuously going on with the same rate. Ice and water are in equilibrium only at a particular temperature and pressure. For any pure substance at atmospheric pressure, the temperature at which the solid and liquid phases are at equilibrium is called the normal melting point or normal freezing point of the substance. Dear student, in the lower classes you discussed what is melting point. This is the temperature at which any solid start to melt. But now you are in the 11th standard. Okay, that's why we have to improve the definition. What is this normal melting point? This is the temperature at which the solid and liquid phases are at equilibrium at atmospheric pressure. Okay, that is called normal melting point. The system here is in dynamic equilibrium and we can infer the following. Both the opposing processes occur simultaneously. Both the processes occur at the same rate so that the amount of ice and water remains constant. Okay, simply we can say the solid liquid equilibrium, the melting point of the solid remains constant at atmospheric pressure. Now come to the liquid vapor equilibrium. A transparent box carrying a U tube with mercury like this. Okay, this is a one box. In this case, this is U tube. This with mercury. We can say this is a manometer. This is used to measure the pressure. Now again you can see in these two limbs of this U tube, the level of mercury is equal. Okay. Now, drying agent like anhydrous calcium chloride or phosphorus pentaoxide is placed for a few hours in the box. Actually, this anhydrous calcium chloride, this is the dehydrating agent, and these are placed. Why? Because if any water vapors or water contents are present in this container, these are absorbed by this anhydrous calcium chloride. After removing the drying agent, a petri dish containing water is quickly placed inside the box like this. This is the petri dish and in this water is there. Now observe. It will be observed that the mercury level in the right limb of the manometer slowly increases and finally attains a constant value. That is, the pressure inside the box increases and reaches a constant value. You can see in this limb, this level of mercury is increased. Starting in initial, this is increases and after some time it becomes constant. It means equilibrium has been reached between the liquid and vapor. And also volume of water in the watch glass decreases. Initially there was no water vapor or very less inside the box. As water evaporated, the pressure in the box increased due to addition of water molecules into gaseous phase inside the box. Initially, the mercury level in right limb is increased because vapors increase. At the same time, water vapors condenses to liquid as the container is closed. That's why these water vapors also start to condense. Okay, and finally it leads to an equilibrium condition when there is no net evaporation. This implies that the number of water molecules from the gaseous state into the liquid state also increases till the equilibrium is attained. That is, at equilibrium, rate of evaporation becomes equal to rate of condensation. Or we can say this reaction can be represented H2O liquid, this state of equilibrium, this is H2O vapor phase. At equilibrium, The pressure exerted by the water molecules at a given temperature remains constant, and this pressure is called equilibrium vapor pressure of water or just vapor pressure of water. Okay, vapor pressure of water increases with temperature because rate of evaporation increases with temperature. Different liquids have different equilibrium vapor pressure at the same temperature, and the liquid which has higher vapor pressure is more volatile. Now, what's the meaning of this more volatile? Higher vapor pressure means lower boiling point. It means easily convert into the vapor phase. Such type of substances are known as volatile substances having low boiling point. Okay. Now, just compare methyl alcohol. This is 64.7 degrees Celsius. This is the boiling point of methyl alcohol. Acetone 56 degrees Celsius and ether 34.6 degrees Celsius. Now, if we compare the vapor pressure of these substances at the given temperature, then we can say ether has maximum vapor pressure because it is more volatile and its boiling point is lower. Is it clear? Time taken for complete evaporation of a liquid depends on the nature of the liquid, the amount of the liquid, and the temperature. When the watch glass is open to the atmosphere, the rate of evaporation remains constant, but the molecules are dispersed into large volume of the room. Now see, that is, we have discussed the closed container in which liquid and vapors are in equilibrium. But if that container is open, what will happen? What will happen? Rate of evaporation remains constant. But as these molecules go in the vapor phase, these disperse into the large volume and rate of condensation will not equal to rate of evaporation. That's why equilibrium will not achieved. As a consequence, the rate of condensation from vapor to liquid state is much less than the rate of evaporation. These are open systems and it is not possible to reach equilibrium in an open system. Okay. Water and water vapor are in equilibrium position at atmospheric pressure, that is 1 atm, and if we express this in bar, then this is 1.013 bar and at 100 degrees Celsius in closed vessel. Okay, the boiling point of water is 100 degrees Celsius at 1.013 bar, or simply we can say at 1 atm pressure. For any pure liquid at 1 atmospheric pressure, the temperature at which the liquid and vapors are at equilibrium is called normal boiling point of the liquid. Now again, dear student, in the lower classes you discuss about boiling point. What is boiling point? The temperature at which any liquid start to boil. Clear? Now this is in the lower class. Now again you are in the 11th standard. That's why we have to modify our definition, and boiling point is the temperature at which the vapor pressure of liquid becomes equal to the atmospheric pressure. If we consider the atmospheric pressure as 1 atm, then that temperature is known as normal boiling point of the liquid. But if atmospheric pressure we consider as a 1 bar, clear, then that boiling point is known as standard boiling point. Clear? Normal boiling point, this is the temperature at which the liquid and vapors are at equilibrium at 1 atm pressure. Clear? Now standard boiling point, this is the temperature at which the liquid and vapors are at equilibrium at 1 bar pressure. And as we know, 1 bar pressure is slightly less than 1 atm pressure. That's why standard boiling point of a given liquid is smaller than the normal boiling point. Okay, for example, the normal boiling point of water is 100 degrees Celsius, that is 373 Kelvin, and its standard boiling point is 99.6 degrees Celsius, that is 372.6 Kelvin. Boiling point of the liquid depends on the atmospheric pressure. As the atmospheric pressure decreases, boiling point will also decreases. Clear? That's why we can say boiling point of any liquid can be changed by changing external pressure. Okay, now this can be applied if we go to the higher altitude. As we know, at the higher altitude atmospheric pressure decreases. That's why boiling point will also decreases. It depends on the altitude of the place. At high altitude the boiling point decreases. Now next one is solid vapor equilibrium. Systems where solids sublime to vapor phase. We know that is sublimation, conversion of solid directly into vapor phase. Okay. Take the one example like solid iodine is placed in a closed vessel. After some time, the vessel gets filled up with violet vapor because the iodine is in violet color, and the intensity of color increases with time. After certain time, the intensity of color becomes constant, and at this stage equilibrium is attained. Hence, solid iodine sublimes to give iodine vapor, and the iodine vapor condenses to give solid iodine. Clear? The equilibrium can be represented like this. I2 in solid state with equilibrium with I2 in vapor phase. Other examples of the solid vapor equilibrium: camphor in solid with equilibrium with camphor in vapor phase. In the same way, this is NH4Cl solid and NH4Cl vapor. Okay student, thank you. Subscribe my channel to get the next video from this chapter.